We are going to present this webinar, Ronald Siat and myself, Roman Martin. This webinar is about advanced nonlinear simulations and structural design. We've been presenting the webinars for all the last year, 2017, and this will be like a resume of all those big capabilities we've seen. And just the reason is because many of you are new, and just to present and have a resume of all the webinars. Before next version, because we are going to launch CivilFEM 2018 in a few weeks. So this is like a resume of all these capabilities before starting with new webinars with the new capabilities. So as you all know, CivilFEM is a general purpose software for any type of civil engineering structural design. So first, CivilFEM is able to solve nonlinear analysis, all type of nonlinear analysis that are needed for civil engineering, and also code and standard checking and design. So CivilFEM is a unique solution for civil structural engineering projects with a mix of intuitive interface, easy to use interface, also with macros, with Python macros, that are able to model complex structure quickly and easy with a range of analysis tools, in static, dynamic, and multi-physics loading scenarios. And well, as I said, the aim of this webinar is to have an overview of these past webinars. Okay, so we will see all these capabilities with these three examples: a high-rise building, where we will try to optimize the steel structure with two different structure types. The classical one with vertical columns and horizontal beams, and also different crosses just to resist lateral loads, and this new structure that is diagonal grid, just to compare both results. With code checking and also pushover analysis, and also we will see fire instability analysis. The second example is a concrete arc bridge with a construction process, and also using concrete nonlinear material models. And the last one is a tunnel building iteration. This is a building that is nearby an old railway. This is in a suburb of a city. And just due to new constructions, this metro railway will be covered. Just there will be a tunnel construction to cover this old railway and to generate new buildings. So we will study how this tunnel affects to this building and to the existing railway, and also slope stability and seismic analysis in this model. So, okay, let's start with the first example, high-rise building. As I said before, we are going to compare classical structures with vertical and horizontal beams and columns, or with this diagonal grid. So let's open the first model. Here it is. So here you can see this is the first example we are going to see, and just this view, you can see there are some internal crosses to support lateral loads, and here inside by the core we have these crosses, you can see inside, and vertical and horizontal columns. So the first step to generate this is defining the geometry, just defining points, lines, and creating it. But also you can create them with different loops and using macros. For that, you have here the script editor here. Then you can here type your commands and your macros. Here, this model, as it is it is the same structure repeated in different levels. You can create different loops and just to generate the model.
Yeah, we can automate all the processes to generate all the floors and all the columns and beams using a very simple Python script.
Well, after generating the geometry, the next step is just going these tabs from left to right, generate the model, select materials. We have selected steel, then the cross sections from library, also by dimensions. We can generate them, and then generate the model, the mesh. After generating the mesh, we apply different loads on the model. Here in the next tab, we create load cases, load groups, and apply to this. We have created two different combinations, the wind load combinations, where we have lateral loads and also self-weight and overloads, and spectral combination. In the spectral combinations, we have a part of the gravity and lift load. We have the response spectral analysis that is included here. So the total combination is generated. This combination is done by these different load groups. For the spectral analysis, here we have the different options. Of course, for checking and design, first we select in the environment, in the first tab, the different codes we will use. In this case, we will use the Eurocode 3, but we have a long list of codes and standards that you can use. American, British, Chinese, Indian codes. Well, you can select any of them and to check and design. Well, after that, after solving, just after generating all the load case, we solve with this some solution properties, and after solve, we open results. Here we are going to open, in example, wind load, the wind load combination. Here we have the wind load combinations, and we can plot different values. In example, in this case, y component of displacement. Here we can see the y displacement. I'm going to select all the model because I unselected a part of it. Okay, well, here you can see in this model we have the first load combination, and the next step is checking. Okay, we will check beams. Here, check beams, check steel beams, and here we have the active code that we have selected and the different checking types, shear, compression, tension, well, all the different checking types that are specified in the active code. We can check this for bending plus axial, and also clicking here, okay, and also we will check for compression backing, and we click here. Okay, after finishing the checking types, we open here and we select the checking design results. So in example, for the wind load for compression backing, we open this, and let's see an example. Well, different results of checking and design. Here, an example, we have this other bending plus axial, and we can plot different results. Example here, total criterion. We can see that the total criterion is 0.9 for compression backing, and here we can see in these columns are these values. We can plot results in the thickness, or also we can plot with these lines.
Yeah, CivilFEM, the total criterion gives you a kind of safety factor. If it's below 1, each cross section is is okay according to the code specification. If it's above 1, it means that the external forces are greater than each cross section resistance.
Well, the steps we have to do to design is just checking, seeing the results, and if we would like, we can check the section dimensions. In example, if we would like to increase any part of these sections, here we have the section that we have previously defined, and we can modify any section. When modifying, the model is updated and we can resolve. So after checking and designing the structure for all the beam elements to be below 1, we can perform the nonlinear analysis. Also, we have done the same steps with the diagrid model. Diagrid from diagonal grid. This is formed by these triangles and these vertical beams in the center. Well, if we get some results of checking results, here we can open checking design results, in example, backlink, compressing backlink, and we also plot total criterion. Here we can see the total criterion is below 5, and we can check where is those, well, in the internal columns, because we can see just that this diagram has a really good behavior for these lateral loads. Here we can see in this plot diagrid versus traditional system. Here we can see for vertical loads how this diagrid works with a vertical axis. This vertical axis is divided into two compression forces and tension forces on bottom. And for lateral loads, these lateral loads will generate a bending moment on the floor that will generate a vertical tension and vertical compression loads. And also we will have the same behavior with these triangles. Here, after designing using checking and design options of CivilFEM, we can perform and plotting total criterion in both. We can analyze the material that is needed in one and the other, and the reduction of the materials, the significant reduction of materials in this structure, analyzing the weight. The next step is generating a nonlinear analysis using the same model. In example, this model. Using this model, just the next step, what we can do is just modify the analysis type of these steel materials and modify it instead of linear by linear. And we can decide between hardening type isotropic, kinematic, or combining between them. And after modifying the behavior, we can apply a lateral load. And open next model, which is the pushover analysis.
By default, always the CivilFEM analyze a linear static analysis, but you can always go beyond. In this case, we started with a linear case and proceeding with a check and design, and now we will add the non-linearity of material. In this case, for steel, but we can do it as well for concrete.
Well, for the pushover analysis, here this is a non-linear model. We apply also large displacements, and here the converging tolerances and the steps we are having. We are having 0.05% of the load on every step. So, well, if we load the results, here we have the results of the pushover analysis until it stops converging. And well, we will see the history plot here from this to this. Okay. We are going to see displacements in one of these nodes versus force that is applied. So if we select one of these nodes, in example 299.
In CivilFEM, you can always plot single results, but in this case, it's very interesting to see in charts how some results are behaving in time or against another value what it's available in CivilFEM.
Well, also we can see there is an elastic behavior of the structure, and then yielding starts happening until the collapse of the structure. We can plot also here in the result, in the last step result, we can plot in example equivalent plastic strain of these elements. And in the equivalent plastic strain, we can see we have some yielding before collapse, and most of the yielding is here in the bottom in some of these columns and also in this diagram. So here, well, you can see the results where yielding is happening. Well, in this way, we obtain, as we have previously seen, the force versus displacement versus force. We can obtain these capacity curves from the models. After obtaining the capacity curves, here the capacity curves of both configurations, traditional configuration and with the diagram one. we can see there are more stiffness, and we can use these capacity curves in an Excel file to calculate the pushover results. The pushover results comparing the demand curve with the capacity curve of both configurations. We can analyze in the points with these curves crosses the state of the buildings. We can see that in the classic configurations we have many yieldings in the point it is crossed, but in the diagram configuration both curves crosses in the elastic region of the building. So it is we can ensure safety of that system. Well, this is a first analysis, non-linear analysis type we can perform in steel structures. But we can go in, this is for the global behavior, but we can go on details on different cross-sections. In the example, analyzing different beams and columns with a non-linear backlink analysis. CivilFEM for this analysis type has different options. First, sorry, this is another, yes. First, if we create a new model, we can perform a backlink analysis. With this backlink analysis, we obtain the backlink shapes. This is a linear analysis. With this backlink shapes, we can update the model. Here we have the next one. Here we can update the mesh using the deformed shape of the backlink modes. Once we have applied a deformed shape on the model, we apply the same vertical loads we applied in the linear analysis, and in this way we can perform non-linear backlink analysis. Next studies we can do in this structure is studying the connections. We can generate models with cells or solid elements, contacts, nonlinear contacts, and modeling bolts and all type of the different components of the connections, and analyze the capacity of these connections. So this is like a resume of some of the options we can have for steel structures. And the last example we are going to see is the stability of steel buildings in fire. This is an example we previously see in the thermal structural couple analysis in a webinar we did, but as you did many questions, we are going to review this example. Well, the first model we have done is a solid element model with solid elements for the protection, fire protection, and inside the column. And we apply the fire temperature outside, solving a transient thermal analysis. And this is the temperature we obtain inside, in the steel part. Well, as we know that this is the temperature that will reach the steel during the different minutes. Instead of modeling the protection in the global structure, what we will do is applying these temperature results of the transient thermal analysis of a detailed model in the global model. So for this temperature that are obtained inside the columns will be applied to the different columns and beams. So we apply directly, instead of applying the protection and applying the temperature inside, we avoid to modeling the protection and apply these curves inside. And we do it in different fire compartments to study, just to analyze possible fires that we could have and if they can generate instability and time for collapse. So for this, we apply these loads first to a possible fire in this zone and a possible fire in this other. So for the first zone, we can see that after some minutes, here drilling start happening. Because in CivilFEM, the thermal structural couple analysis, materials are time-dependent properties, so temperature properties. The elasticity modulus is reduced and yielding is happening in this part. But collapse doesn't happen. For next example, for next part, fire is in this part. So we can see that after a minute it is yielding and collapse in the structure happens. So this could be useful for knowing the time we need for evacuating the building, or if we have to reinforce different parts with a better fire protection. Well, next example we are going to see is a concrete arch bridge. This bridge, we will see first the construction process in CivilFEM. Then the construction process is based on different cables that are pre-stressed. So we will use a macro for cable pre-stress calculation. After that, we can perform code checking and design, similar to the previous model, and also use nonlinear concrete material. So the construction process has first a first stage that is using the different arc parts are just tied by cables to the top of this pile, and also the top of this pile is tied to this bottom. After that, after this first part of the arch is generated, a tower here is constructed, and then this point is used to hold the last part of the arc. Once the arc is finished, the cables are removed and we put the deck. So here we can see this construction process.
In this case, we are using a very powerful tool of CivilFEM, which is the activation and deactivation of materials for these construction processes or construction stage analysis.
Well, for that, as Ronald said, what we have done is using here, we generate different structural elements. This is the first part that is generated. This is the second, third, and so on. If we select all the model, here we can see the first part, second, and so on. So well, here what we are doing is that we use a different material on every part. Even if that is the same concrete, we use different materials. The first one here you can see is C4050 for phase number 1. So here in these materials, phase number 1, we see that the activation time is day 13. This is the day we are placing the concrete in this part. So we can play with activation and deactivation time. And after that, when solving, here you can see the load cases we are solving. What we do is just solve different phases of the construction, and what we add is a calendar time. This calendar time is 39 days, in example. So as the activation time of this material is, as we saw before, here is 30 days, and we are solving for 39 days, it means that when we are solving this material age is 9 days. So in this way, we activate and deactivate. For example, for this cable is the material is this one, phase 1, and what we are doing is that it's activated in day 13, the same day that this part is generated, and then we deactivate it in day 130. That is the day when all the arc is finally constructed. Okay, so if we solve the model in this way, we can see an example. I'm going to select just a part of the model. That is, in example, the load case, the construction phase 9, number 9, in example. And we plot the results. We are going to plot some results here. Results here, open. And this is, we are plotting the stage 9. So for the stage 9, we are going to plot, in example, vertical displacement. We are seeing that here we have 2 centimeters vertical displacement. Also, if we analyze the model, considering not only elastic deformation, but also creep and sink rates, for considering creep and sink rates, we have to activate this to creep step by step and sink rates by temperatures. We apply, CivilFEM apply equivalent temperatures to have the same sink rates effect. And depending on the active code, we have here different properties that are defined by the codes and standards. Relative humidity, equivalent thickness, creep coefficient, and here we have the table for creep coefficients that can be modified by the user. So we can see that considering creep and elastic deformation, we have here 2 centimeters. So what we are going to do is calculate pre-stressing on every of these cables to make the vertical displacement equal to 0. So we can do it manually, solving and just modifying and solving again until vertical displacements on all these points, on this where the cables are anchored. Just we can do it manually. But for this case, what we have done is using a macro. CivilFEM can use macros, as you know, Python macros, and well, it's very easy to use them. For calculating the vertical displacement, what we do is a loop here. With this loop, I add it from 1 to 10, but it will stop before. Just I can add here a big number, and what I do is just creating a parameter vertical displacement 1 for the phase 2. That is the first part of the arc that is generated in the state 2, and with this command results, I get no results in the control node that I have defined different control nodes at the end of these cables, and what we read is vertical displacement. Then, if the vertical displacement is greater than 0, it means there are vertical displacements. I increase the pre-stressing force and apply this pre-stressing force to the load group cable 1. So with this loop, we are resolving the model and recalculating vertical displacements until vertical displacement is greater than 0. I increase this force with this loop 50 by 50. So you can see with a simple loop, well, this is not the total macro, this is a simple loop for the first cable. I will have to repeat this loop 9 times for the 9 cable groups. And if we see the difference in results, here you can see that we have vertical displacements here, 2 centimeters, but if we open the same value after applying this macro, that is applying the right pre-stressing, we can see here results are just a few millimeters, less than 5 millimeters. In my loop, I added a tolerance of 0.5 centimeters. So the macro is working until the value is less than 0.5 centimeters, positive or negative. So here you can see the different parts. Also, an example for this node here, that is 15,288. We can see the history of the displacement from phase 1 to phase 10. That is the construction process of the arc. We add here node result. Here is vertical displacement, and in centimeters. So we can see that the number 1528, and we plot it. We can see the displacement we are having just 0.15 positive, because well, you know the range I apply is 15, and then it's reduced till this value during the construction process. If we load the other values without pre-stressing, we can see this value, it's much higher. Here we can see how displacement is increased till some centimeters. So after calculating with the creep and syncreep properties, we also can define different non-linearities. One of them is cracking and crashing. Just for seeing that, I will use some slides. Well, before going to that, you can see here comparing vertical displacement with and without pre-stressing. You can see here vertical displacement is less than half centimeter, and here 3 centimeters. Also, these cables can be used with unpressed stress cables like this for carrying concrete to the different parts and to calculate this cable for the cranes. So here, if I display, you can see how the deformed shape, vertical displacement due to different loads. So also unpressed cables can be used in CivilFEM. For the after solving different load steps, in example this one, what we can do is performing code checking. I'm going to check in example, well, here in the cross sections we defining. You can see we have here defining the cross section with reinforcement. If we plot it, this is the arc cross section with the reinforcement. So we can perform checking, different checking for beams. In example, we can perform axial plus bending, also shear and torsion, and also cracking. So if we perform a bending plus axial, here we can see the different options of this checking, and we perform here, we check it, and we can plot these results. Checking results, and this is the phase number 10, and bending plus axial. And we plot the total criterion. We see the total criterion is less than 1, so it means it is okay. So we can perform a bending plus axial using the interaction diagram. Also, we can perform a cracking checking, and also we can also perform the design options. An example for the desk of the model, I'm going to load the last load step.
The process is very similar to the steel elements that we have been performing in the steel structure. Yeah, at the end, but in this particular case of the concrete, we work with reinforcement. So we can ask the software to check or verify the reinforcement that it is added and defined, or we can ask the software how much or maybe we need more or less reinforcement to get an okay section according to the interaction diagram, which depends on the material pivots and that.
Well, in this case, what we are doing is designing instead of checking design cells. So what we are doing is design by the orthogonal direction method, and the orthogonal to normal directions in X and Y, normal and longitudinal of the decks. Here we have different options to neglect torsional and membrane forces. We are going to consider for the bending plus axial, we are going also to consider the torsional and in-plane shear. So we are going to calculate reinforcement considering axial plus bending plus in-plane shear plus torsional moment. So clicking OK, we generate their design results. So here we can see these design results that are a reinforcement amount at X top. We plot it, X is longitudinal. We can see the reinforcement amount in X top is needed for the negative values in the supports over the piles. But in bottom, X bottom, it's in the mid of the different spans where this reinforcement is needed. So you can check and design the concrete structures using these options. But also we can perform nonlinear analysis with the concrete. CivilFEM, well, here you can see those reinforcement amount results in square centimeters per meter, 11 and 21 in different parts. Well, for the nonlinear concrete material behavior, first we have the option to activate cracking and crushing. When we activate cracking and crushing, we have this material law behavior. For the principal stress, when we have tension, when the tension reaches the cracking tension, there's a softening modulus that is defined by the user where the stresses are being reduced and the strains are being increased. CivilFEM just add these strains after cracking as crack strains. We can plot those crack strains, and you can see in this beam model these crackings due to the shear effects on bolts and to the bending in bottom, very similar to the theoretical part. And for compression, we follow this parabolic load. Here in CivilFEM you can see the parabolic load that are defined by the AFTID code, until we reach a deformed, a low-level deformity, that is the crashing strain. When we reach the cracking strain, the element crashes. And also activating cracking and sink rates. We are going to see in concrete here in the model where to activate that in one of these concretes. First, we click here for cracking, and we activate cracking options. And well, I can define a new material, an example just for you to see. Concrete material. I select any of these, this is an example. And here cracking, I activate cracking, and then crashing. This is the critical shear, the cracking tension stress, shear retention, and the softening modulus. And also I can activate cracking. For compression, we have these parabolic rectangular loads that are defined by the AFTID code. We can modify them if we would like. And also here, creep and sink rates, we can activate creep and also sink rates. So we can have a completely nonlinear concrete behavior. Here if we see some examples of these models, here on the left we can see that we have a 2D model, stresses on top and cracking strains on bottom. So we can see this is a half of the beam that is modeled with vertical loads, and we can see that when cracking happens, just stress, normal stress is modified. We can model these concrete materials. We can model these concrete materials with solid elements, and we can define the bars inside it with bar elements or beam elements that are supporting bending or not, with the nonlinear behavior. So we can apply different loads, and we can obtain also yielding on the reinforcement. So we can apply dynamic analysis. And here in this part, we are seeing just also a beam, a 3D beam with a vertical loads, and just cracking are happening on the model, considering reinforcement and also pre-stressing. Because CivilFEM also has pre-stressing utilities. Pre-stressing, the tendons can be defined with cable elements inside a model, but also you can use the pre-stress concrete options, the equivalent loads that has CivilFEM. They work with beam, shell, and solid elements. CivilFEM automatically calculates short and long-term losses and apply equivalent forces. These equivalent forces can be applied considering any layout of the tendons inside beam, shell elements, or solid elements. These are loads that can be combined with the construction process or any other type of loads, and after that you can check for axial plus bending, shear, and cracking checking. So here you have a model that this is a foundation slab with pre-stress, and here you can see results as they apply this pre-stress and the different loads. You can see here reinforcement amounts, and this is a silo with vertical and circular tendons. CivilFEM calculate losses and apply equivalent loads.
Yeah, we had a very interesting past webinar. You can always check our YouTube channel, and but of course, you can propose always a new examples for our upcoming webinars.
Okay, well, let's see the last example. The last example is just a tunnel building iteration. We have seen concrete and steel structures. We will see now the geotechnical material models and the different options for soil structure iterations, and also slope instability with nonlinear material models. So well, the first step is just as I explained before, this is the old railway here that is by a building. So well, the new building plan in this area is to cover this, make a big road here, and create to generate new buildings. And a tunnel is going to to construct under this, but the railway needs to be kept in use. So trains are coming here, also this building, so we are going to see the affection of this tunnel to both the railway and the building. And any possible, if there is big displacement or any type of affection, any type of reinforce the soil to avoid it. And also slope instability to see the safety factor of this before and after the tunnel construction. So while CivilFEM has several geotechnical material models like Tucker Powder, Morculon with variable cohesion and friction angle, tensile concrete models, well, we will have Hook and Brown this year, and of course initial stress state. With these material models, we are able to model different soil behavior, like normal consolidation soils with these parabolic curves, over consolidation soils, just a bit over consolidations with this bilinear. When the pre-consolidation stress is reached, the curve is different, and extremely consolidation pressures that we have this type of behavior. We are able to model them with camp clay, and to do these typical problems with J-lin are generated in the model, where we can calculate the load capacities and different type of problems. Well, here you can see the construction process in the model, and we are plotting vertical displacements in both. So you can see that the vertical displacement are affecting to all this area. This is a 2D cut in the model, and just to be able to see it here. And you can see the affection on top of the building. So we can see this model, and we can see different results. I'm going to close models. And
here the number of elements, as you can see, are increased due to the soil and the foundation. Yeah, well, depending on your license, you will be able to model it or not.
So well, the excavation process is done in the same way. In example here, the first part of the tunnel is using the soil excavation #1 material. So if we go to soil excavation #1 material, we can see that is deactivated construction process start in the day 59. After it is excavated, just we have mortar around it. If we just unselect it and select for the, in example, load case 3 or 4, we can see we have here in the model different layers. We are excavating different parts, and we have here the rings of the layer, the different rings that are placed by when the tunnel is constructed, and between the rings, the precast rings and the soil, a mortar is injected. So this mortar has different times for activating and deactivating. So what we do is generate the different parts with different materials. In these materials, we add an activation time, different activation times, and the activation times, and we solve for different calendar times. And just in this way, we solve the tunnel construction process. For the soil, we are using non-linear material models. In this case, we use Drucker bracket with a cohesion of 15 and a friction angle of 15 kilopascals. So we will see during the construction process the affection to the building. So if we load the load case, and we are going to plot different results. In example, we are going to plot vertical displacement on this node. No vertical displacement. 2, 8, 9, X, and vertical displacement instead of
You can always plot any result which is stored in CivilFEM. Not only one, you can plot different ones at the same time.
Well, here we can see the vertical displacement during the different excavation phases. When it starts, we have not match displacements until well, we are plotting this node here in this part. So we can see we are generating 4 centimeters downwards displacement in this soil during the construction process. Let's see in the building, in example, this node here, we are going to generate, let's see, horizontal displacements, and this node is 1,6,1,6,5, and we plot in this case horizontal displacements. We can see that the building has 2 centimeters horizontal displacements. So well, this is very big, and we are going to analyze different possibilities of just for avoiding these big displacements. One of the solutions that we have proposed is adding a line of piles. Here we can see, well, we are going to see the video as this model is generating. Here we can see the construction process and the vertical affection, and we are going to generate a line of piles in front of the building that are digged on this hard rock to protect the horizontal displacement of the building. Also, another analysis type that we are doing is calculate the slope stability. For the slope stability, for these nonlinear material models, we are using the shear strength reduction method. This method consists in dividing the strength of the material. In this case, we are solving with Mohr Coulomb. So Mohr Coulomb strength is defined by cohesion and friction angle. With the cohesion and friction angle, we have the yielding surface, that is this in black. What we are doing is dividing these values, cohesion and friction angle, by a factor. So the yielding surface is being reduced until the model collapses. So the model collapses when the failure occurs, that is the instability of the model, we obtain the safety factor. So this factor is increased until collapse. If we see we are doing this slope stability analysis in the first stage before tunnel construction. So we can see here that a yielding surface can happen here for a safety factor around 2. Here you can see the yielding zones. So this building has a safety factor around 2. And the second option is solving after the tunnel construction. We can see the yielding parts are much bigger, and there is an interaction between the building, the tunnel, and the yielding zones. So we can see the safety factor is reduced. So it is needed, we need to reinforce these zones. What we will do is adding here some piles from top till the hard rock. So if we see here the model, here we plot all the structural elements. Here we can see we have generated a line of piles. If we remove this terrain, here we can see the piles that are generated here. Also, here you can see that this building is just inside the terrain. It has 2 underground floors, parking, and we have contacts between soil and the structure. We can have different type of contacts. To define a contact is very easy. Here, first in the mesh, we can generate contacts, and we decide contacted. Contacted, in example, is zone, the soil, and the soil. We click it, and then clicking here, we define the contacting. The contacting is the foundation and the lateral walls, in example. So in this way, we define our contact, and after that, we define for cells, as we are having cells for this, if we are considering both faces and thickness or not considering thickness. And the type of contact. Glue contact, it means it's always in contact. Touching contact, this is a frictional contact, so we have to define a friction value. and also a limit for friction stress. If that friction stress is higher, there will be slippage, and also breaking and advanced contacts, where we define a cohesion and a friction angle. Well, we don't have much time because we are finishing the time we have, but well, here you can analyze, as you have seen, different options for reinforcing, and also these piles. These piles will have some reinforcement. Here we can plot. And we can also check and design these piles and check if the displacements are lower. So, well, using again the slides, here we can see slope stability. And, well, also here we have other model where we have applied seismic analysis. We can also, to this nonlinear model, apply transient analysis with accelegrams. We can apply accelegrams or displacements on the contour of this model. Also, we can use damping boundary conditions for the models, and then apply the transient nonlinear analysis and check yielding surfaces. Well, as a summary, you can see that CivilFEM 2017 has a lot of advanced features, just like code checking and design by codes and standards, the most important codes all over the world, and also nonlinear analysis such as nonlinear backlink, pushover, nonlinear material models, cables, nonlinear contacts, and all these nonlinearities works with static responses, static transit analysis, and also we have response and harmonic analysis. And with all this type of analysis can be mixed also with couple analysis, that is seepage and thermal structural couple analysis. We have seen an example of thermal structural couple analysis with the building and fire, a transient nonlinear thermal structural couple analysis, and in a future webinar we will see the seepage, the couple seepage structural analysis with water tables and seepage variable seepage in the transient seepage in the model. And well, as you can see, CivilFEM is a general purpose software ideal for any analysis and design of any type of civil engineering structure. That can solve any problem that civil engineering, structural engineering will have in their life. Well, as you have seen, CivilFEM lowers the barriers for nonlinear problems and all civil engineering projects, combining advanced nonlinear solver, MARC and advanced nonlinear solver from MSC software, and a friendly, easy-to-use graphic interface, and also Python macros of CivilFEM that solving very important problems from single to multiple nonlinearities.
Well, to continue with the services of INCESIBER, and to know more about CivilFEM and the finite element analysis, finite element method, INCESIBER provides you many solutions, many services. One of them is the International Finite Element Analysis Masters, which is hosted by INCESIBER and UNED and the Open Spanish University, which has more than 20 years of experience. Here you can check this website. Always take into account that we have two branches, one for ANSYS products, CivilFEM for ANSYS, and the family of the CivilFEM or MARC MSC software.
Well, here in this webinar you have seen some global capacities of CivilFEM. The target of this webinar is just to present the options you have, but you also have different options to learn about finite element method with this master. Also, if you would like to practice, you can download an educational version, a free educational version, and we also have some videos that are focused on how to use the software. So this webinar is how to just show global capacities, but we have other videos about how to use the software, and of course we have this master just to learn about finite element method.
Yeah, this includes fundamentals, theory, and practice. But if you want to just focus on practice, there's another website, which is the International Computer-Aided Engineering Education Center. This is the website where you can see many courses. In this case, using CivilFEM to getting started with CivilFEM and another software. Another interesting website is you can see our next upcoming webinars or past webinars, and check always our YouTube channel of CivilFEM. Another, due to the upcoming release of the 2018 version, as Roman explained before, which will be in the next weeks, we're inviting you to know this new version by being part of this beta tester program. It will take 1 month, starting on this March, and all the users will have interesting rewards depending on how you will take on this beta tester. You will get some prizes. This is the website, and always stay tuned to our media, and we will give you more info. And I think there will be some questionnaire at the end. So if you are interested, you can
yes, well,
say yes.
Yes, I would like to remark that we have done like a resume of previous webinars. We will have the next webinars you can check in our website. We'll have the next webinar for next version that we are having, 2018, coming soon. We will have the next webinar will be the highlights of the new version, and a webinar after this will be the advanced C-page structural copy analysis with geotechnical applications. So this will be also a very important webinar for seeing CivilFEM capabilities.
Yes, and if you want more information about commercial and sales, you have these contacts, our support, and another reminder of our e-learning courses.
Also, if you would like any special demo for you or see in details some of the examples we've seen today, just you can ask us for a demo.
Please, if you have just a minute, you can complete a survey which will appear once you exit this webinar. So thank you very much, and see you soon.
Bye. Thank you very much for your attention.
Bye-bye. Thank you.